Okay, now we're going to talk about analyzing graphs of functions. Now again, some of this is overlapping material, just new notation or new terminology here. So the first thing I want to remind us, I'm not going to go through and write the definition down here, is that the graph of a function must pass the vertical line test. Now, a couple videos ago we already talked about what the vertical line test is. Um, so yeah, kind of redundant here to talk about it again, but it is something important to say. You know, the graph of a function must pass the vertical line test. Alright, so let's move on to the next topic here. And this is actually, we're going to have several videos on it, and this is actually going to be the only major topic on this video, and it's the zeros of a function. And so let's talk about the definition here. So the zeros of a function are the x values that make f of x equal 0. Now again, I just want to emphasize, and we've actually done this calculation, I think even we did this in the last video here, we just didn't use the terminology zeros. We said find x when f of x equals 0. But again, the key thing here you want to think about is the zeros of a function correspond to the x-intercepts. Alright, so let's just look at a couple examples here. Now, the examples we're going to look at here, one thing you have to be careful about finding zeros of functions is making sure that they're in your domain. And so we're going to look at some examples of some functions. First, what we're going to do is write the domain down, and then find the zeros, and then make sure that the zeros are actually in our domain. Okay, so let us start here with, so this is going to be the same for all of these examples. Find the zeros of the following functions. Alright, so let's start with g at t is equal to the square root of t minus 25. Now, as I said, what we're going to start with all of these here is writing down what the domain is. So my domain, well, what do we know? This is a square root, so t minus 25 has to be greater than or equal to 0. So t has to be greater than or equal to 25. So my domain is all real. All real numbers t such that t is greater than or equal to 25. Alright, so that's my domain. Alright, so let's go ahead and find out when this thing is 0. We kind of have already done that, but it's important to get the domains down, and we'll see this in another example. Alright, so we want to set this function equal to 0. So I'm going to have 0 is equal to the square root of t minus 25. Now remember, solving radicals, we've talked about how to do that. You want to raise both sides to the appropriate power, and since this is a square root, I'd raise both sides to the second power. So you'd have 0 squared equals the square root of t minus 25, quantity squared. And so then we get 0 equals t minus 25. Add both sides, 25 to both sides, and you get t equals 25. Now, we should check, is t equal 25? Is 25 part of the domain? Yes, the domain is all values t such that t is greater than or equal to 25. So that is okay. So this is my 0 here. And there's only one. So the 0 of g at t is just t equals 25. Alright, let's look at another example here. Let's look at h at x is equal to x squared minus 9 over x minus 1. Now, let's again write my domain down. So the domain here, we can see kind of by inspection, this is just all real numbers x except x equals 1. So I'm going to now still solve this just like I would normally. I'm going to set h at x equal to 0. So I have 0 is equal to x squared minus 9 over x minus 1. Now, just like I would solve these kinds of equations before, I want to kind of clear out the denominator. So I'm going to multiply both sides by x minus 1. But one thing I'm going to emphasize here is that x is not equal to 1. And I'm emphasizing that here off to the side because if x was 1, we'd be multiplying both sides of the equation by 0, which basically destroys your equation. So, and that's kind of just going back to domain, because we have to make sure whatever answer we get doesn't have 1 with it. Alright, so then we get, doing that, of course 0 times x minus 1 is 0. So I'd have, and then these x minus 1s would cancel. So we get 0 equals x squared minus 9. And then this factors x minus 3 times x plus 3. So the zeros of h at x are 3 and negative 3. I guess I didn't actually write down x equals 3 and negative 3, but it's pretty obvious once you get it factored. Alright, I want to look at one more example, and actually we're going to wrap this video up then. It's going to be a shorter video than some of the others, but one more example here, and this is going to try to illustrate why we need to care about the domain and knowing what x is allowed to be and what it's not allowed to be. So let's look at this. F at x is equal to x squared minus 4 over x minus 2. So the domain here, pretty obvious from inspection. Domain is all real numbers x except x equals 2. Alright, so we're going to go ahead and solve this just as we did the other ones. So I'm going to have 0 is equal to x squared minus 4 over x minus 2. Then clear out the denominator. So I'm going to multiply both sides by x minus 2. And again, I'm going to put that note here that x can't be 2. Of course, when I multiply there, the x minus 2's would cancel. 0 times x minus 2 is still 0, so you get 0 equals x squared minus 4, which means you get 0 is equal to x minus 2 times x plus 2. And so we'd wind up with x is equal to 2 or negative 2. However, remember, x can't be 2, so that means even though I got that answer there, that's not one of my zeros because it's not in the domain. So the 0, there's actually only one for this graph or this function. So the 0 for f at x is x equals negative 2. Now, there is another way we could have done this problem, and we'll talk about that when we get into rational functions, which we'll get into later on in the semester. So as I said, this video is going to be a little bit shorter. We're not done talking about analyzing graphs of functions. Just the next couple topics I know are going to be a little bit longer.